Hi there, you're in the lab with me, JJ. Today is Old Book Teardown Day. We're going to be tearing down an old book. So the job title for today is Circuit Breaker. Today I'm the Circuit Breaker. This is the book we'll be tearing down. It's another book in the series from McGraw-Hill called the Electrical and Electronic Engineering Series. It's the Electrical and Electronic Engineering Series. This particular book is written by John D. Ryder, and it's called Engineering Electronics. Looks like it's got a number for the Dewey Decimal System or something. I don't know. Anyway, it looks like it's been in a real actual library. There's various cancelled. Oh, here we go. North Sydney Technical College. So it used to be part of their library, obviously, but they cancelled it and they must have sold it or something. Anyway, it ended up with me. The full title is Engineering Electronics with Industrial Applications and Control. And John D. Ryder was a PhD. He was Dean of Engineering and Professor of Electrical Engineering at Michigan State University. Awesome. Published by McGraw-Hill Book Company, New York, Toronto, London, 1957. 1957. So that's a while ago, isn't it? Anyway, what we'll be doing today is just jumping over the bench here and flipping through this and having a bit of a squiz at what's inside. We won't be reading it closely, we're just going to have a look in there and see what's there. So let's pop over to the bench and see what's in our book.
Here on the bench, and here is our tome, hardcover. It says on the front, McGraw-Hill Electrical and Electronic Engineering Series by John D. Ryder, Engineering Electronics, McGraw-Hill, 261.34.26. I don't know what that is, maybe G or 8 or something like that. There's a number on the back, 54364. I don't know what that means. There's this cancelled stamp has been put everywhere. Okay, I don't know what that means. Ryder J.D., Engineering Electronics with Industrial Applications and Control. Okay, don't know why they needed to write that in there. It's here. Anyway, so this is part of the McGraw-Hill Electrical and Electronic Engineering series. The consulting editor was Frederick Emmons Terman, and associate consulting editors were W.W. Harmon and J.G. Truxell. So, looks like a lot of books. Alternating current machinery, acoustics, analysis of feedback control systems, theory and application of industrial electronics, synthesis of linear communication networks, volumes 1 and 2, harmonics, sidebands, and transients in communication engineering, introduction to nonlinear analysis, fundamentals of vacuum tubes, control system dynamics, foundations of information theory, basic electrical engineering, electric machinery, basic electron tubes, fundamentals of television engineering, engineering electronics. That's what this one's called, but it's got a different subtitle. Fundamentals of electronic motion, introduction to electromagnetic engineering, engineering electromagnetics, fundamentals of electrical engineering, electronics in engineering, transmission lines and networks, antennas, electromagnets, analysis of alternating current circuits, general network analysis, electronics, pulse and digital circuits, introduction to electric fields, transient performance of electric power systems, engineering electronics, that's this volume, electron tube circuits, electronic engineering, introduction to electromagnetic fields, radio electronics, direct current machinery, electric transmission lines, transient electric currents, fundamentals of electron devices, vacuum tubes, elements of power system analysis, passive network synthesis, electronic and radio engineering, electronic measurements, elements of servo mechanism theory, servo mechanism analysis, alternating current and transient circuit analysis, automatic feedback control system synthesis. Wow. And this is the title page, Engineering Electronics with Industrial Applications and Control, written by John D. Ryder, PhD, Dean of Engineering and Professor of Electrical Engineering at Michigan State University. It used to be at the North Sydney Technical College Library, and they cancelled it. And then we've got McGraw-Hill Book Company, Inc., New York, Toronto, London, 1957. So there we go. There's that number again. I don't know what 54364 means. I don't know. It's got something to do with the Maple Press Company. Interesting. Here's a preface from the author. We'll have a read of that. Okay. Preface, John D. Ryder. Electronics, employing basic knowledge and the dynamics of electric charges. Did you hear that? Thunderstorm. Electronics, employing basic knowledge of the dynamics of electric charges and their physical behavior in conductors, circuit and network theory, electromagnetic fields, and feedback and control theory, is profoundly influencing all areas of electrical engineering. Formerly somewhat restricted to the higher frequencies and to the transmission of information, electronics has now invaded the industrial and business areas, and a broader viewpoint is needed. This text attempts to supply the basic knowledge required by those working in the broad, non-radio portion of the electrical engineering field. Many arbitrary decisions have been made to include or exclude material since, while the radio portion of the field of electronics is rather specifically bounded, no such bounds have been found for the industrial or engineering electronics area. Because of this undefined breadth, it has not been possible to study applications in great deal, and this has aided in preventing the work from becoming a handbook of operation of specific circuits and apparatus. The first 3 chapters provide a survey of electronic devices and concepts for those without previous training. Fundamentals of semiconductors and the transistor are covered in Chapter 12. Throughout, frequent recourse is had to mathematics and circuit theory to provide a quantitative understanding of the subject. All right, so they knew transistors were coming at this point, but it sounds like they're going to be telling us about tubes as well. What do you reckon? Here's the table of contents. What have we got? 18 chapters, starting with Chapter 1, Introduction. All right. Contents preface, which we just read. Chapter 1, Introduction. The atom and the electron. Development of the vacuum tube. Gas tubes. Solid state developments. 2. Physical phenomena in electron tubes. Action of electrons in electric fields. Current flow in space. Action of electrons in magnetic fields. Electrons in metals. The surface energy barrier and electron emission, thermionic cathode materials, thermionic cathode types, photo emission, secondary and high field emissions, space charge effects in the thermionic diode, current control by a grid, the vacuum triode, energy losses and cooling in vacuum tubes, ionization in gases. Chapter 3, the vacuum tube as a circuit element. Nonlinear volt-amp characteristics, vacuum triode current and voltage notation, triode graphical characteristics and triode parameters, the dynamic transfer curve, graphical analysis of circuit performance, the voltage source equivalent circuit for a triode, the current source equivalent circuit, gain of an amplifier, measurement of tube parameters, the tetrode, the pentode, the beam tube, the variable mood tube, self-bias and amplifiers, voltage sources, distortion of waveform, classification of tube operating conditions, the decibel in gain measurement, the cathode ray tube, and oscillograph. Chapter 4, Small signal amplifiers as circuit elements. Basic amplifier types. Coupling of cascaded amplifiers. Input admittance of a triode as a grounded cathode amplifier. Grounded cathode amplifier analysis. The cathode follower amplifier. Design of cathode follower circuits. Analysis of the modified cathode follower. The grounded grid amplifier. AC operation of voltage amplifiers. Chapter 5. Response of small signal amplifiers. Frequency and phase response of the grounded cathode amplifier. Further study of the frequency and phase response of the RC amplifier. Steady state decibel gain plots. RC circuits for alteration of bandwidth. Factors affecting amplifier bandwidth. Low frequency compensation of RC filters. That's RC amplifiers. High frequency compensation of the RC amplifier. Pulse response of the RC coupling circuit. Relations between sinusoidal and pulse response. Square wave response and testing. Fourier series. Analysis of a recurrent rectangular pulse. Noise in amplifiers. Chapter 6. Low frequency power amplifiers. Output circuits for low frequency power amplifiers. Load line construction. Load line for reactive loads. The ideal Class A amplifier. Power relations. Theoretical limit on Class A efficiency. Determination of amplitude distortion. Intermodulation distortion. Choice of load for optimum power output. The distortion rule. The push-pull amplifier. Bias consideration in push-pull amplifiers. Equivalent circuit for the push-pull amplifier. Graphical analysis using the composite tube characteristics. The Class AB push-pull amplifier. The Class B push-pull amplifier. Design of Class B amplifiers for large power output. Grid circuit power requirements. Signal sources for push-pull amplifiers. Chapter 7. Feedback in amplifiers. Feedback principles. Negative feedback and gain stability. Negative feedback and distortion. Negative feedback and noise. Feedback measured in decibels. An example. Basic negative feedback circuits. Other feedback circuits. Positive feedback, decoupling. Stability of feedback amplifiers. Further discussion of stability conditions. Chapter 8. Direct coupled amplifiers. Computing amplifiers. Early direct coupled amplifiers. The resistance coupled amplifier. Cathode coupling in DC amplifiers. The balance push-pull amplifier. Cathode drift compensation. Series cathode compensation, the bridge balanced amplifier. Vacuum tube electrometers. Residual drift in direct coupled amplifiers. Chopper modulated amplifiers. Chopper stabilized direct coupled amplifiers. The operational amplifier. Use of positive feedback. Analog computation. Lagrange's equation for dynamical systems. The direct analog computer. Scale factors. Functional or operational analog computers. Function generators. Nonlinear circuit elements. Limiting circuits. Multiplying devices and circuits. Chapter 9. Switching circuits. Digital computation. Circuit elements. Tubes in switching circuits. Response of RC and RL series circuits. The time constant. The differentiating circuit. Integrating circuits. Clipping circuits. Clamping circuits. Clamping in the television system. The ringing circuit. The blocking oscillator. Time base or sweep generation for cathode ray tube deflection. Simple RC sweep generation. thyratron sweep generators, triggered vacuum tube sweep generators, linearization of the RC sweep, other forms of time bases, sweep circuits for magnetically deflected cathode ray tubes, the free-running multivibrator, effective bias, synchronization of the multivibrator, the one-shot multivibrator, the trigger or flip-flop circuit, scaling circuits, decimal scaling circuits, the decade counter tube, the binary number system, digital computers, computer input and output, memory or storage facilities, vacuum tube gating circuits, diode switching matrices, and or not circuits, addition logic. Chapter 10, power supplies and filters, voltage regulators, the half-wave diode rectifier, the full-wave rectifier, ripple factor, the shunt capacitor filter, the series inductor filter, the L section or inductor input filter, the bleeder resistor and critical input inductance, capacitor input filters, voltage multiplying filters, voltage multiplying rectifiers, rectifier circuit design, voltage regulator, VR tubes. Of course, these days VR is virtual reality, not voltage regulator. You can still do voltage regulation, of course. Vacuum tube regulators, AC regulators, voltage references. Chapter 11, oscillators and Class C amplifiers, high frequency heating, waveforms in Class C amplifiers, analysis of Class C amplifier performance, power relations, the resonant load circuit, frequency multipliers, feedback in oscillators, circuit criteria for feedback oscillators, basic feedback oscillator circuits, electron coupling, crystal control, phase shift oscillators, ultrasonic oscillators, electromagnetic fields in metals, skin effect in metals, induction heating of cylindrical bars, heating of dielectric cylinders or slabs, power required for rapid heating, heating power calculations, oscillators as high voltage DC sources, semiconductors, transistors. That's chapter 12, semiconductors, transistors. Semiconductors, energy levels and conductivity in semiconductors, the p-n junction, junction and point contact diode rectifiers, the point contact transistor, the junction transistor, transistors and vacuum tubes, 4 terminal networks, equivalent circuit for the common base amplifier, the common emitter circuit, the common collector amplifier, summary of transistor amplifier characteristics, graphical analysis of large signal transistor performance, bias and stabilization, cascaded amplifiers, frequency response of the RC amplifier, push-pull and complementary symmetric circuits, instability in point contact transistor circuits, transistor feedback oscillators, negative resistance oscillators and triggers, the tetrode transistor, large area rectifiers, and thermistors. All right. So they talk about the point contact transistor. I think that's just a bipolar junction transistor. I think that's what we'd know that as today. And they mention the JFET, junction transistor, the junction transistor. I don't know if that's a field effect transistor or what. And they talk about the tetrode transistor. But the tetrode is a tube, not a transistor. So maybe there's a silicon, a semiconductor thing that can act like a tetrode, maybe? I don't know. We'll have to pay attention to that when we get to chapter 12. Maybe we'll learn something. So to chapter 13, photoelectric devices and applications. Light, cathode materials, the vacuum photoemissive cell, or the phototube, the gas-filled phototube, phototube relays, phototube circuits for measurement purposes, use of modulated light, electron multipliers, the photovoltaic cell, the phototransistor, and light amplifiers. Chapter 14, Power Rectification. It's going to take a break. Chapter 14, Power Rectification. Arc discharges, thermionic cathodes in gas discharges, mercury pool cathodes, mercury vapor tube characteristics and ratings, arc back, basic half-wave gas diode rectifier, full wave and bridge rectifiers, parallel operation of gas diodes, three-phase half-wave rectifier relations, M-phase rectifier, M-phase rectifier relations, transformer utility factor, M-phase rectifiers with inductance filters, effect of transformer reactance, the three-phase bridge circuit, double Y rectifiers, polyphase branched connections, performance. Chapter 15, Power Control and Inversion, the thyrotron, ionization and deionization times, grid current in thyrotrons, the gas tetrode or shield grid thyrotron, bias control of average current, phase shift control, combined phase and bias control, the phase shifting bridge, saturable reactor control, pulse control of thyrotrons, the ignitron firing circuits, controlled thyrotron or ignitron rectifiers, control of alternating current, ignitron ratings, switching gas triodes with DC anode potential, gas triode counting circuits, inverters, the transistor inverter. Chapter 16, Relays, Timers, and Resistance Welding Controls. The contact relay, DC operated time delay relays, AC operated time delay relays, time interval measurements, the resistance welding process, automatic sequence timer, synchronous weld control, follow-up or trailing tube circuit, timing the weld, heat control, energy storage welding systems, polyphase welding systems, electronic motor control, DC-DC motor relations, thyrotron supply for the DC motor, speed-torque relations, speed regulation by armature voltage control, IR drop compensation, field weakening, armature current limiting, auxiliary controls, speed control by tachometer, control of low torque AC motors, phase selective circuits. Chapter 18, Servo Mechanisms. Servo mechanisms and control, first order servo mechanism, second order systems, transient response of a second order system to a step input, derivative control, error rate control, integral control, temperature regulator with integral control, sinusoidal response of a second order system, transfer function analysis, transfer function for multiple loop feedback, transfer functions of several circuits, transfer function of several physical elements, AC motor servo system, stability criteria, gain and phase margin, example, further Nyquist plots, other systems. Then we have the index beginning on page 655. They've got their stamp here. They didn't click cancel on that one. So, chapter 1, Introduction. The science of electronics is fundamental to a vast area of electrical engineering. Certainly, the development of this science must be given credit for the useful application of frequencies above a few hundred cycles and for the wide application of non-sinusoidal waveforms. Electronic knowledge is now employed in devices operating from zero frequency to tens of thousands of megacycles, handling powers from microwatts to thousands of kilowatts, and employing a great variety of the infinitude of waveforms. In this text, it is proposed to emphasize the scientific principles of importance to the area known as industrial or engineering electronics, usually associated with the lower frequencies and dealing quite largely with the signals and methods leading to the control of energy in some form, as contrasted with the concept of transmission of information more often associated with the field of radio. 1.1. The atom and the electron. Present atomic theories based on the atom model. Oh, that was just a power surge. My UPS devices seem to survive it. That's good. I'll be back in a sec. Sorry, there's an electrical storm here and the power is dropping in and out. So hopefully the UPS devices do keep everything online. So far, so good. Let's just continue. So I'll just go back to where we were. So, the atom and the electron. Present atomic theories based on the atom model proposed by Bohr place the mass and positive charge of an atom in a central nucleus surrounded by moving electrons. The nucleus is composed of neutrons and protons. Neutrons have a mass approximately 1/16 that of the mass of oxygen atom and have zero electrical charge. They occur in fixed numbers in all nuclei except that of hydrogen. The proton has a mass slightly lighter than that of the neutron and approximately equal to the mass of the hydrogen atom. It has a charge equal to that of the electron, but positive in sign. The chemical elements are differentiated by varying numbers of protons and neutrons in the nucleus, the number of protons being equal to the atomic number, hydrogen having 1, helium 2, and so on. Since the atom is in electrical balance in its normal state, the number of associated electrons moving around the nucleus is equal to the number of protons. The electron is the smallest known indivisible unit of electric charge. Early experiments succeeded in measuring the ratio of the charge of the electron to its mass, and in 1910 the charge was first measured, thus determining these properties of the electron. Repeated experiments have refined the values for these constants of the electron, and they are now believed to be charge, known as E, is 1.602 times 10 to the minus 19 coulombs, and the mass, M, of the electron is 9.106 times 10 to the minus 31 kilograms. Charge per unit mass is E on M equals 1.759 times 10 to the 11 coulombs per kilogram. Wow. Imagine having a kilogram of electrons. That's a lot. The electron appears to have a dual personality, at times being best thought of as a particle, and in other experiments seeming to require wave properties for a satisfactory explanation of the phenomena. This duality is not yet fully understandable. When wave properties are assigned, the electron wavelength is related to its velocity as lambda equals h divided by mv meters, where h is Planck's constant, which is 6.624 times 10 to the minus 34 joule seconds. M is the electron mass in kilograms. V is the electron velocity in meters per second. Electric current is due to movement of electric charges, frequently electrons. However, long before the existence of the electron was known, it was customary to speak of electric current as due to movement of positive charges from positive to negative in a metallic circuit external to the source. This usage is too well established to be readily overcome, even though it is now known to be reversed, with the negative electrons moving from negative to positive in the external metallic circuit. Therefore, when electric currents are discussed, the customary direction will be meant. When reference is made to electronic current, then the flow of electrons is being considered. The photon is also important as a fundamental particle. It is a bundle of radiant energy or light, the amount of energy being related to the frequency as W equals HF joules. The amount of energy carried by any given photon thus depends on its frequency. This particle also shows duality in character and must be considered as having wave properties in discussing many optical experiments. The photon, while not having a material mass, may be considered as having a radiation mass, and this equivalent mass is related to the photon energy by the Einstein equation W equals mc squared joules, where c is the velocity of light, which is 3 times 10 to the 8 meters per second, roughly. Development of the vacuum tube. Okay. The first use of a vacuum tube probably occurred with the discovery of the Edison effect by Thomas A. Edison in 1883. During an experiment with an incandescent lamp, Edison discovered that a current would flow through the evacuated space from a heated filament to a small metal plate when the plate was positive and cease to flow when the plate was negative, indicating rectifying properties. This current discovered by Edison is now known to be due to electron flow from the heated element to the positive electrode. In 1897, J. A. Fleming in England, after hearing of the work of Edison, applied the Edison effect to the detection of or rectification of radio signals in a diode, which became known as the Fleming valve. In 1907, Lee de Forest added a grid or control electrode to the Fleming valve and made the highly sensitive relay device now known as the triode or 3-element tube. A very large amount of research in vacuum tubes, electron emitter materials, and circuit design was required before the triode could be fully exploited. These developments included pumps capable of really high vacuums, thoriated tungsten and oxide-coated emitters, and circuit and tube designs suited to a wide range of applications. Around about 1926, the difficulties due to internal element capacities, which prevented useful amplification at frequencies higher than about 1 megacycle, caused Dr. A. W. Hull to add a 4th electrode, the screen grid, to the triode, making the tetrode or 4-element tube. A few years later, he added a 3rd grid or suppressor to the tetrode, making the pentode, to overcome certain deficiencies in tetrode operation. This latter type has properties which make it highly desirable over a very broad frequency range, and it is now one of the most generally used tube types. Many other specialized forms are available and will be discussed in connection with their applications. All right, then we're going to talk about gas tubes, solid state developments. There exists a large class of materials which have electrical properties falling between metallic conductors and insulators. These materials are called semiconductors and show interesting electrical properties which are largely due to a shortage of current carriers. These materials exhibit negative temperature coefficients of resistance, and it is found that they may conduct by use of negative characters or electrons, or by positive characters, the absence of electrons, called holes. Silicon, germanium, selenium, and titanium compounds have are a few of the materials exhibiting these unusual properties. Crystal rectifiers employing some of these materials have been in use in radio since the beginning of the century. Recently, it has been discovered that control or relay properties are possible, leading to triode and tetrode forms of a semiconductor control device known as the transistor. Because of the lack of a need for a heated electron source and possible long life as a result, these devices are of considerable interest for various industrial applications. Oh yeah. Now up to chapter 2, physical phenomena in electron tubes. Electron tubes are nonlinear circuit devices and operate as they do because of a number of physical phenomena which occur inside the tube, such as emission of electrons, the action of electrons in fields, limitation of current by space charge, the effects of initial velocities of the emitted electrons, the energy delivered to the electrons, and ionization of any gas present. These physical processes impose limits on the practical operating ranges of electron tubes. Since an understanding of tube properties and the proper application of tubes are both so dependent on these physical processes, it seems desirable to survey the phenomena inherent in electron tubes in this chapter. All right, now we're going to talk about the action of electrons in electric fields. Bunch of mathematics for us there. Talk about current flow in space. Talk about the action of electrons in magnetic fields. Okay. Talk of electrons in metals. Talk about the surface energy barrier and electron emission. Thermionic cathode materials. Thermionic cathode types. Cathode types. Inverted V, inverted W, spiral heater cathode, folded heater, heat shielded cathode. Photo emission. Secondary and high field emissions. Space charge effects in the thermionic diode. Current control by a grid, the vacuum triode. Energy losses and cooling in vacuum tubes. Ionization of gases. Sorry, that's ionization in gases. And we got some problems, some references. Oh, look, there was a fire. Look at that. This page has been burnt. Wow. The vacuum tube as... I bet you there's a story behind that. What do you reckon? You reckon it was a lab mistake or a cigarette mistake? Who knows? This book is a little bit yellow. All right, up to chapter 3, the vacuum tube as a circuit element. Nonlinear volt-ampere characteristics. Vacuum triode current and voltage notation. Triode graphical characteristics and triode parameters. The dynamic transfer curve. Graphical analysis of circuit performance. The voltage source equivalent circuit for a triode. Gain of an amplifier. Measurement of tube parameters. The tetrode. The pentode. The beam tube. The variable mood tube. Self-bias of amplifiers, voltage sources. Distortion of waveform. Classification of tube operating conditions. The decibel in gain measurement. The cathode ray tube and oscillograph. And we got problems and references. Small signal amplifiers as circuit elements. Basic amplifier types. Actually, I'll read you the introduction. Small signal amplifiers as circuit elements. The performance of a vacuum tube, be it triode, tetrode, or pentode, is dependent on the particular circuit configuration with which the tube is employed. As 3-element devices, tubes may be connected into 4-terminal input and output circuits in 6 different ways, only 3 of which have so far had much practical value. These 3 basic circuit forms differ as to gain, input and output impedances, and external circuit loading, and each circuit must be studied in some detail. For this study, the tube will be considered as a linear circuit device under the equivalent circuit assumption, and therefore only small signal tubes will be considered. Basic circuit performance will be studied in this chapter. Response of these circuits as functions of input frequency and waveform being deferred to chapter 5. Basic amplifier types. Coupling of cascaded amplifiers. Input admittance of a triode as a grounded cathode amplifier. Grounded cathode amplifier analysis. Cathode follower amplifier. Design of cathode follower circuits. Analysis of the modified cathode follower. The grounded grid amplifier. AC operation of voltage amplifiers. We got problems and references. Chapter 5. Response of small signal amplifiers. In the previous chapter, the amplifier in its several forms was studied in general as a circuit element without regard to the manner in which the tube or load reactances might affect its output response with changes in input frequency or waveform. The analysis and design of amplifiers for steady-state operation over wide frequency ranges and also with pulsed inputs will now be undertaken. The internal tube capacities and coupling circuits employed to separate the AC or varying and DC output from components introduce reactive circuit elements and thus possibilities for frequency and phase distortion. A great variety of waveforms must be handled by amplifiers, and the frequency and phase characteristics must be carefully designed to avoid distortion in operating over wide bands of frequencies. Frequent use of pulses or rectangular waves illustrates the need for wide frequency ranges, since from the steady-state viewpoint, harmonics above the 100th are required to preserve rectangular and pulse forms. Intermittent pulsed waveforms also may not permit the attainment of a steady state, and the response of circuits to each isolated pulse must be determined if waveform is to be preserved. Thus, for linear small signal amplifiers, the circuit designer must consider frequency and phase response on a sinusoidal basis and transient response to pulse and other non-sinusoidal waveforms. The design of amplifiers with suitable responses is discussed in this chapter, largely in terms of the RC-coupled grounded cathode circuit because of its wide adoption. Extension to other amplifier forms follows by application of the material of chapter 4. Then we do frequency and phase response of the grounded cathode amplifier. Further study of the frequency and phase response of the RC amplifier. Steady-state decibel gain plots. RC circuits for alteration and bandwidth. Factors affecting amplifier bandwidth. Low frequency compensation of RC amplifiers. High frequency compensation of the RC amplifier. Pulse response of the RC coupling circuit. Fourier series. Analysis of a recurrent rectangular pulse. Noise in amplifiers. And we've got problems and references. Low frequency power amplifiers. In many applications involving vacuum tubes, appreciable power output is required and large input signals are applied to obtain that power. Graphical performance analysis must then be used, since the dynamic transfer characteristic will usually not be linear over the whole of large grid voltage excursions. This nonlinearity may create amplitude distortion, and operating conditions to prevent or reduce such distortion are available. In other cases, where the tube operates merely as an AC or DC power switch, distortion is not important and operating conditions are fixed by allowable currents and internal tube power loss. Since the vacuum tube is a loss-limited device, high power handling efficiency is important. Class A operation is normally employed when minimum distortion of waveform is desired. However, if some distortion can be tolerated, the operating efficiency and power output of a given tube can be increased by Class AB operation. Push-pull operation reduces distortion from either Class A or Class AB operation and makes possible high power output Class B operation. Thus, a designer must select the class of operation, a tube with sufficient plate dissipating rating, and then determine the proper load resistance, the DC supply voltages, the input signal required, and the resultant distortion if this is a critical matter. And we're on to output circuits for low frequency power amplifiers. We've got load line construction and load line for reactive loads. Got some scope traces here. This is figure 6.5. Square waves applied to transformers 1 and 2. $20 cycles, 100 cycles, 1,000 cycles, 10,000 cycles, 20,000 cycles. That's interesting, isn't it? Low cost unit on left, large unit on right. Yeah, all right. Power relations. Determination of amplitude distortion. Intermodulation distortion. Choice of load for optimum power output. The distortion rule. Bias considerations in push-pull amplifiers. Equivalent circuit for the push-pull amplifier. Graphical analysis using the composite tube characteristics. The Class AB push-pull amplifier. Class B push-pull amplifier. Design of Class B amplifiers for large power output. Grid circuit power requirements. Signal sources for push-pull amplifiers. Problems. References. Feedback in amplifiers. While the principle of feedback, or the comparison of the output of a device with its input to improve the accuracy of the output-input relation, has been previously applied in the process control and other industries, a real understanding of its effects, and in particular its application to electronic amplifiers, was not available until H.S. Black published an important paper in 1934. This served to mathematically formalize the field of feedback, and the applications of this mathematical analysis have now made possible a real understanding of the control of physical processes in many fields, as well as creating usable and accurate servo mechanisms, process controls, and vacuum tube amplifiers. The vacuum tube alone is an uncertain and variable electronic device. Combined with negative feedback, it becomes a precise and dependable engineering tool. Feedback principles. Negative feedback and gain stability. Negative feedback and distortion. Negative feedback and noise. Feedback measured in decibels, an example. Basic negative feedback circuits. Other feedback circuits. Positive feedback decoupling. Stability of feedback amplifiers. Further discussion of stability conditions. Problems. References. Chapter 8. Direct coupled amplifiers. Computing amplifiers. In much measurement work, it is desirable to retain the DC components, initial displacements, and the like that may accompany the AC components or varying signals. Amplifiers which will amplify down to DC or zero frequency as one limit are then required. Since such amplifiers cannot employ reactive coupling elements, phase shift and frequency distortion are absent up to those frequencies at which the internal tube and stray shunt capacities become effective. A tube in a direct coupled amplifier, however, is unable to distinguish between an input DC signal and a shift in its bias voltage, so that direct coupled amplifiers introduce special problems in stability, and methods of overcoming these difficulties will be discussed here. Certain forms of direct coupled amplifiers are also employed for performing mathematical operations in electronic computing machines of the continuous variable or analog type, and these circuits will be introduced. While the direct coupled amplifier is able to amplify direct voltages, the term, as abbreviated, DC amplifier, means a direct coupled amplifier and not necessarily a direct current amplifier. Okay, a direct coupled amplifier, not necessarily a direct current amplifier, since it's quite possible that a direct coupled amplifier may be used to amplify alternating current only. Early direct coupled amplifiers. The resistance coupled amplifier. Cathode coupling in DC amplifiers. The balanced push-pull amplifier. Cathode drift compensation. Series cathode compensation, the bridge balance amplifier. Vacuum tube electrometers. Residual drift in direct coupled amplifiers. Chopper modulated amplifiers. Chopper stabilized direct coupled amplifiers. The operational amplifier. Analog computation. Oh, hang on. Use of positive feedback. Okay. Then analog computation. Lagrange's equation for dynamical systems. the direct analog computer, scale factors, functional or operational analog computers, function generators, nonlinear circuit elements. While vacuum diodes, triodes, crystal diodes, and some special materials such as thyrite will yield nonlinear volt-ampere characteristics, stability and reproducibility are somewhat lacking. Building up of nonlinear characteristics by addition of straight line segments is more accurate and stable, and such a process is possible with reasonable numbers of crystal diodes employed only as switches. The process is illustrated in figure 834, where 3 straight line segments are utilized to approximate a volt-ampere curve. The conductances required for each segment are... Okay. Oh, that's interesting. Okay. If suitable switching be provided at O, E1, and E2 to place the proper conductances in the circuit. Limiting circuits, multiplying devices and circuits, problems, references, switching circuits, digital computation. Okay. In previous chapters, the ability of the vacuum tube faithfully to amplify a given input voltage has been studied and emphasized. It is now necessary to introduce another large class of vacuum tube circuits in which emphasis is on the ability of the tube to operate as a switch. In this latter class, the output voltage may bear no relation to the input magnitude or waveform except to be present or absent in accordance with certain levels of input. The vacuum tube thus used is an inertial-less and nearly instantaneous switch, having speed of operation as its main advantage. Its major difficulty is that when enclosed, it still represents a small but appreciable resistance. When open, of course, it has a resistance which is essentially infinite. The low value of closed resistance must be allowed for in circuit design, but can be neglected in many cases. Circuits employing vacuum tubes as switches are frequently used to generate pulses and other non-sinusoidal wave shapes, or to operate with or by such pulses or waveforms. Radar equipment forms one such class of circuit, with television, digital computers, and various pulse-modulated communication systems also included. All right, and we're going to talk about circuit elements, tubes in switching circuits, responsive RC and RL series circuits, the time constant, the differentiating circuit, integrating circuits, clipping circuits, clamping circuits, clamping in the television system, the ringing circuit, the blocking oscillator, time base or sweep generation for cathode ray tube deflection, simple RC sweep generation, thyrotron sweep generators, triggered vacuum tube sweep generator, linearization of the RC sweep, other forms of time bases, sweep circuits for magnetically deflected cathode ray tubes, the free-running multivibrator, synchronization of the multivibrator, the one-shot multivibrator, the trigger or flip-flop circuit, scaling circuits, decimal scaling circuits, the decade counter tube, the binary number system, digital computers, input control memory output, and arithmetic unit. There you go. Computer input and output, memory or storage facilities, vacuum tube gating circuits, diode switching matrices, and or not circuits. There we go. And or not. Huh, that's good fun. Addition logic, problems, references, power supplies and filters, voltage regulators. Since almost all electric power is generated as alternating current, it is necessary to rectify that current when DC supplies for amplifiers and electronic equipment are desired. This is the common practice for the supply of plate potentials for electron tubes, vacuum diode rectifiers usually being employed. The half-wave diode rectifier, the full-wave rectifier, ripple factor, the shunt capacitor filter, the series inductor filter, the bleeder resistor and critical input inductance, capacitor input filters, voltage multiplying rectifiers, voltage regulator VR tubes, vacuum tube regulators, AC regulators, voltage references, problems and references. Chapter 11, oscillators and Class C amplifiers, high frequency heating. The conversion of DC power to high frequency power, either in oscillators or in amplifiers, is an important duty of the vacuum tube. Since very large amounts of power are handled in these circuits when applied to high frequency heating of metals and dielectrics, power efficiency is important and the tubes are operated under Class C conditions. In this service, the tubes act as synchronous switches, connecting DC sources and load for small angles of conduction each cycle. The resonant loads then continue in free oscillation for the remainder of the cycle. Because of the continuous nature of tube conduction in Class C amplifiers, an equivalent circuit approach is not possible, and graphical methods have been developed for analysis of Class C operation. And we've got waveforms in Class C amplifiers. The Class C amplifier is operated with a bias of 2 or more times the cutoff grid voltage. A resonant circuit load or tank circuit is used in the plate circuit, tuned to the frequency or some multiple of the grid input. With the grid well below cutoff, only a small portion or angle of the positive grid input voltage will drive the tube into conduction, and the conduction angle will be less than 180 degrees, occurring from theta 1 to theta 1, or negative theta 1 to theta 1 as shown in figure 11a. The resonant load in the plate circuit excited by these short current pulses will go into oscillation in accordance with basic electric circuit theory and develop a sinusoidal voltage across the tank. Analysis of Class C amplifier performance. Prediction of performance of Class C circuits with particular tubes is based on a knowledge of current and voltage waveforms present, determined from the tube characteristics by a graphical method. This approach is made necessary by the discontinuous nature of current flow. The method suffices to predict desirable or optimum values for load impedance, grid bias, and AC grid driving voltage, grid input power, and plate loss. Power relations. The resonant load circuit. Feedback, frequency multipliers, feedback in oscillators, circuit criteria for feedback oscillators, basic feedback oscillator circuits, electron coupling, crystal control, phase shift oscillators, ultrasonic oscillators, electromagnetic fields in metals, plenty of math on those pages, and more. Skin effect in metals. If the cylinder of figure 1118 be made of a good conductor, certain simplifying assumptions can be made. In particular, it can be shown that, sigma is much greater than omega epsilon at even the highest attainable frequency, and thus equation 1144 may be written for metal as gamma squared equals negative j omega mu sigma. Wow. Induction heating of cylindrical bars. Heating of dielectric cylinders or slabs. Power required for rapid heating. Heating power calculations. Oscillators as high voltage DC sources. Problems. References. Chapter 12. Semiconductors, transistors. The properties of semiconducting crystal rectifiers have long been employed in radio reception. These semiconductors, with properties between those of good conductors and those of insulators, have recently been more thoroughly investigated, and this research has led to further applications, and particularly to the transistor, a semiconductor control device having amplifying as well as rectifying properties. The transistor is able to perform the functions usually assigned to the triode vacuum tube, although it is at present limited to a few megacycles as an upper frequency limit for amplification and has a higher internal noise level. The vacuum tube is a voltage controlled device, while in contrast, the transistor is current controlled and is in fact the circuit dual of the vacuum tube. This duality aids in understanding transistor performance by analogy, but the concept should not be carried to extremes. The transistor boasts a major advantage over the vacuum tube in that it requires no cathode heating power. With lower internal impedance, levels, it is operable at lower applied voltages than the vacuum tube, giving greater overall power efficiencies. Since there is no emitting cathode, very long life is anticipated for transistors. Analysis and design of transistor circuits follow the pattern already discussed for vacuum tube circuits, provided due consideration is given to the requirements for operating impedance levels and the fact that the transistor has a finite input impedance even at low frequencies. The parameters of the transistor will be discussed and similarities to the vacuum tube pointed out without repetition of the applicable circuit analysis and design methods of preceding chapters. Then we're off. We're going to talk about semiconductors, and then it'll be the p-n junction. No, energy levels and conductivity in semiconductors. Okay. Oh, here we go. And there's the p-n junction. I knew that was coming. Junction and point contact diode rectifiers. The point contact transistor In 1948, Bardeen and Brattain reported on work with a second point contact on a germanium diode, which showed that when the second contact was biased in the reverse direction, its current could be controlled by the current through the forward biased first rectifying contact. They called the resulting solid state 3-electrode device the transistor. The forward bias electrode is called the emitter, the reverse bias electrode being the collector, and the germanium or silicon element is the base, as shown in figure 1212. The unit uses an N-type semiconductor wafer about 0.5 millimeters thick, and the two wire contacts are spaced about 0.05 millimeters apart. The positive bias on the emitter immediately removes electrons from the valence bonds near the surface, creating holes. In fact, the emitter is said to inject holes into the semiconductor, and the emitter current is composed of electrons. The holes immediately diffuse towards the negative collector. In the process, many holes may meet and recombine with the free electrons in the N-type base material. To reduce this loss of holes, the emitter and collector must be close spaced. Holes that reach the collector area combine with excess electrons injected into the region by the collector, and this permits the reverse bias collector to inject more electrons, increasing the collector current to the base. The holes, in traveling from emitter to collector by random paths, set up a positive space charge. This space charge attracts more electrons from the collector and serves to further increase the electron flow from the collector. While some of these electrons serve to neutralize holes, the majority flow toward and reach the base terminal, forming a base collector current. The mobility of electrons is about twice that of holes, so that a hole is, on the average, able to neutralize the charge due to about 2 electrons, and the collector current may be expected to have a ratio of electrons to holes of about 2, with a total collector current about 3 times the emitter current. It may also be seen that this collector current depends on the number of holes injected at the emitter and can be controlled by the emitter current, since otherwise the current to the reverse bias collector would be very small. The ratio of a change in collector current DIC to a given change in emitter current delta IE with collector voltage constant is called the short circuit current amplifier factor alpha CE. This is in the limit given here. All right. From the above discussion, it would be expected that alpha CE for a point contact transistor would be about 3. This ratio may not be reached, however, because of recombination in transit, and usual values are in the range of 2 to 3. There are also examples in which alpha CE may exceed 3. Understanding of this phenomenon is not yet complete, but it is believed due to properties developed near the collector by the forming operation. A point contact transistor can also be made from P material. The emitter is forward biased but negative, the collector back biased and positive. The input resistance of the emitter base circuit is low, if the order of 100 to 500 ohms. Because of the forward bias, the output resistance between collector and base is relatively high because of the back bias, and of the order of 10,000 to 50,000 ohms for point contact units. For a unit with ACE equals 2.5, input resistance of 300 ohms, and a load of 20,000 ohms, the voltage gain may approximate 160 and the power gain 400 or 26 decibels. Thus, even with a low current gain, the voltage and power gain from a transistor may be large because of the difference between input and output impedance levels. Then we've got the junction transistor. A germanium or silicon crystal may be grown with 2 N regions separated by a very thin, that's 0.002 centimeters, P region, or with welded or fused P regions on a very thin N section, thus forming NPN or PNP junction transistors. Oh, bipolar junction transistor. Oh, they talk about, so, okay. So this is your, these must be now what we call bipolar junction transistors, BJTs. For the junction construction, the first diode or emitter junction is biased in the forward direction. For the NPN unit, this means the emitter is negative and thus the emitter junction potential barrier is lowered, as shown in figure 1214b, in contrast with the unbiased level in figure 1214a. Electrons enter the N region from the emitter, and those of higher energy are able to pass over the small barrier into the P region. The barrier height and the number of these high-energy electrons reaching the P, or base, region are a function of the emitter base potential. In this operation, the emitter barrier acts as an electron velocity or energy filter, much as does the grid in a vacuum tube. Some of the electrons, possibly a few percent, combine with holes in the hole-rich region, but because the base is very thin, most electrons passed onto the N-type collector region under attraction of the back biased but positive collector, and these electrons constitute the collector current. Though the emitter collector current amplification factor alpha CE may have a value approximating 0.95, amplification occurs because electrons injected through the emitter into a low impedance forward bias circuit are extracted at the collector at a much higher impedance level. The collector potential is made high enough so that a small reverse current ICO flows with zero emitter current. Ordinarily, ICO is small with respect to IC, the total collector current. It is found that ICO does not vary appreciably with VC, the collector base voltage. The current ICO is highly temperature sensitive since it is due to intrinsic conduction and may become of appreciable magnitude at high operating temperatures. Okay. Transistors and vacuum tubes. With some equivalent circuits here. Very good. 4-terminal networks. Equivalent circuit for the common base amplifier. The common emitter circuit. The common collector amplifier. Summary of transistor amplifier characteristics. Graphical analysis of large signal transistor performance. Bias and stabilization. Cascaded amplifiers. I think these days we'd call that the Darlington pair. That doesn't seem to be a term they're using here though. Frequency response of the RC amplifier. Push-pull and complementary symmetry circuits. Instability of point contact transistor circuits. Transistor feedback oscillators. Negative resistance oscillators and triggers. The tetrode transistor. Thermistors. The rapid variation of resistance with temperature for certain semiconductors is employed in the thermally sensitive resistor, or thermistor, to measure temperature. Mixtures of various metallic oxides are used to give units with useful resistance variations in desired temperature ranges. In one type, the resistance varies about 4% per degree Celsius at room temperature, and the resistance may change by a factor of 10 to the power of 3 in a 300 degrees Celsius range. Thermistors are made of small beads or rods with wire leads and bead diameters down to 0.015 centimeters or 0.006 inches. It has been found that many such units obey an exponential law of the form given. We've got problems and references. We're up to chapter 13, photoelectric devices and applications. Photoelectric release of electrons or conduction by impact of light, as discussed in chapter 2, is employed in 4 basic types of cells. These are photoemissive cells or phototubes, employing the phenomena of emission of electrons when light strikes a cathode of low work function material. The sensitive surface is enclosed in an evacuated or gas-filled envelope of glass or quartz, the electrons being captured by a positive anode. Photovoltaic cells, in which the radiant energy striking the sensitive surface causes generation of an EMF. With proper design the short circuit current can become an almost linear function of the incident light flux. Okay, that's photovoltaic cells, which we use for power. Photoconductive cells, which vary their electrical resistance from a high value in the dark to a low value when exposed to light. They consist of a thin coating of selenium on a glass plate. An early form, they are now rarely used and will not be discussed here. Okay, and phototransistors, in which the semiconductor properties of germanium or silicon are varied in accordance with incident light. Light is the name given to radiant electromagnetic energy having wavelengths roughly in the range from 0.01 to 100 microns, where the micron is 10 to the minus 6 meters and is abbreviated by the symbol mu. Wavelength may also be stated in terms of the angstrom unit. A equals 10 to the minus 10 meters, or the millimicron equals mu equals 10 to the minus 9 meters. The frequency of the light may be calculated from the wavelength through use of the velocity of light. C equals 2.99776 times 10 to the 8 meters per second, which approximately equals 3 times 10 to the 8 meters per second. And you can do that. Frequency equals the speed of light divided by the wavelength, where the wavelength lambda is in meters. The extremes of the wavelength range stated above lie at the far ultraviolet and the far infrared. Intermediate between these limits is the visible range, extending only from 0.4 mu in the violet to 0.7 mu in the red end of the spectrum. Luminous light flux is that portion of the radiant energy which produces a visual sensation in the human eye. Since the sensitivity of the human eye is not uniform to all colors in the visible range, being most sensitive in the blue-green near 0.53 mu, the eye cannot be used as a standard of intensity measurement. The output of a photoelectric cell may be stated in terms of current output per unit of total radiant power striking the cell surface. This is frequently given as microamperes per microwatt of incident power over a specified color or wavelength range from a given source. The color or wavelength range or the source must be stated, since the conversion efficiency of various photoelectric cathodes varies radically with incident wavelength. A standard source for comparison purposes is frequently a tungsten lamp operating at a temperature such that its spectrum of radiant energy is that of black body operating at 2870 degrees Kelvin. The relative distribution of energy at different wavelengths for a tungsten filament operating at this color temperature is shown in figure 13.1. There you go. Cathode materials. The vacuum photoemissive cell or phototube. The gas-filled phototube. Phototube relays. Phototube circuits for measurement purposes. Use of modulated light. Electron multipliers. The photovoltaic cell. The photovoltaic cell generates an electromagnetic force upon incidence of light. Such cells consist of a layer of a semiconductor on a metal-based plate and are of two types, either copper oxide or copper or iron selenide on iron. It's copper oxide on copper or iron selenide on iron. The semiconductor may be covered by a thin film of a transparent conducting lacquer. Circuit connections are then made to the base and to a spring contact made on the periphery of the lacquered area, as indicated in Figure 13.13. That's here. Upon incidence of light energy, electrons are given enough energy to pass across the forbidden energy gap, and if the semiconductor is placed on a metal base, these high energy electrons can flow over into the metal. As long as the illumination continues, there is supply of these electrons in the conduction band and current continues. The voltage generated is of the order of a few hundred millivolts in bright light, and this voltage is not a linear function of light flux. The cell resistance is small, and in sunlight, currents of a few milliamperes may flow. It is found that the short circuit current is a linear function of light flux, as indicated in Figure 13.14, and is proportional to the total light flux or number of photons received, as might be expected from the conduction theory. If a small resistance, such as that of a microammeter, is used as a load, the response is approximately linear with light, and the instrument may be calibrated in terms of incident illumination. This is the application in the photographic exposure meter. The current may also be used directly to operate sensitive relays for illumination control, such as in school classrooms. Since spectral response may closely follow that of the human eye, this is a desirable control application. Cells of this nature are sensitive to high temperature, and the selenide cell may be damaged if operated above 55 degrees Celsius. Fortunately, it is found that both EMF and internal resistance are temperature functions, so that the short circuit current is nearly independent of ambient temperature changes. Since the photovoltaic cell develops such a small DC voltage, amplification directly by vacuum tubes is not suitable, except by a chopper amplifier. Use with modulated light must also be limited to very low frequency because of the shunt capacity between semiconductor and base. This layer is so thin that the capacity so high that the output may be reduced 1/2, even with the 60 cycle variation. Photovoltaic cells may be connected in parallel to increase the total area and the total received light flux and the output current. They may also be connected in series for working into high resistance loads. Then we're going to talk about the phototransistor and light amplifiers, and then problems and references. Up to chapter 14, power rectification. To provide large amounts of direct current in industry, it is customary to employ the mercury vapor or gas-filled diode as a rectifier. The gas diode is well suited to industrial application because of its large current capacity and high power efficiency. Because of special characteristics due to the gas present, and because the electric power is usually supplied at 3 or more phases, the operating characteristics and circuits differ from those of Chapter 10, where single-phase low-current rectifiers for supply of electronic amplifiers were studied. In industrial applications, a filter circuit is rarely needed, owing to tolerance for considerable ripple, and if employed, can be simpler than those previously studied because of the higher ripple frequency occasioned by polyphase operation. We've got arc discharges, thermionic cathodes in gas discharges, mercury pool cathodes, mercury vapor tube characteristics and ratings, arc back, basic half-wave gas diode rectifier, full wave and bridge rectifiers, parallel operation of gas diodes, three-phase half-wave rectifier relations, M-phase rectifier relations, transformer utility factor, M-phase rectifiers with inductance filters. Effective transformer reactance. The three-phase bridge circuit. Double Y rectifiers. Polyphased branch connections. Performance, problems, and references. Chapter 15, Power Control and Inversion. It has been found possible to control the starting time of the arc discharge by means of a grid in the hot cathode gas diode and thereby add a form of electrostatic control to the advantages of high current capacity and high efficiency already held by that device. The result of the addition of the grid by Langmuir and Hull was the thyratron tube, meaning the door tube. Later, Slepian developed an electrical starter for the mercury pool cathode tube, eliminating the need for the slow-acting mechanical starters in circuits where control of starting of the tube was desired. This device was called the ignitron. Emission is always present in the thyratron, whereas the igniter element in the ignitron provides the initial spark and electrons. In the thyratron, the grid prevents the arc until it is desired, while in the ignitron, the arc is started when desired. These inventions have opened a new field of control, equivalent in many ways to that by the vacuum tube, but at a much higher level of power and efficiency. We're going to talk about the thyratron. Ionization and deionization times. Grid currents in thyratrons. The gas tetrode or shield grid thyratron. Bias control of average current. Phase shift control. Combined phase and bias control. Phase shifting bridge. Saturable reactor control. Pulse control of thyratrons. The ignitron. The ignitron was developed by Slepian in 1933 to provide a fast electrical starter for the mercury pool type of tube. It utilizes a graphite anode, pool cathode, and an igniter electrode, all contained in a steel envelope. For small sizes, these are pumped and sealed off, but large units are usually operated continuously connected to vacuum pumps to remove any gases which may be released during operation. Most sizes are water jacketed for removal of heat developed in the tube during operation. Figure 1520 shows a cutaway view of one type of ignitron. Ignitron firing circuits. Controlled thyratron or ignitron rectifiers. Control of alternating current. Ignition ratings. Sorry, that's ignitron rating. Ignitron ratings. Switching gas triodes with DC anode potential. Gas triode counting circuits. Inverters. A circuit that will change direct to alternating current is called an inverter. Gas tubes are well suited to such operation at the lower frequencies owing to their high power efficiency. The circuits of figure 1534 operate on direct current and provide alternating voltages that may be modified by insertion of an output transformer as in figure 1536. There you go. The transistor inverter. This is it here. It's got a couple of coils, a couple of diodes. I don't know why it's called an input inverter if the value out is not AC. There is frequently a need for conversion of low voltage direct current, as from storage batteries, into direct current suitable for supplying the high voltage filter systems of electronic apparatus. This has been done in the past by electromagnetic vibrators, chopping the DC input and rectifying the AC output, but contact difficulties may lead to short life. An inverter or feedback oscillator employing power transistors with adequate cooling has been found useful, and one form is illustrated in figure 1539. Windings L1 and L2 are the transistors are connected as a common base push-pull feedback oscillator, winding L2 providing the feedback. The resultant AC output is coupled out by L3, stepped up to the desired voltage level, and then rectified by the germanium diode bridge. The frequency of operation is determined by the inductance and saturation effects in the transformer and is usually in the 60 to 100 cycle range. The transistors operate at a 50% duty cycle, being cut off half the time, and with good cooling conditions are reported to have given outputs of several hundred watts at overall efficiencies of 80%. And then we've got problems and references. Chapter 16, Relays, Timers, and Resistance Welding Controls. Relays are used where a small amount of power must control a large power, and this is a requirement well met by the electron tube. Important applications of vacuum and gas tubes are found in the operation of electrical contacts with small current and in the timing of various operations. For time intervals of a few seconds to many minutes, it is common to employ a synchronous motor-driven switch. For less accurate control, a bimetal strip and heating element or a thermistor may serve over the same range of time. With time intervals of a minute down to a fraction of a second, the vacuum tube controlled by transient voltages in an RC circuit is usual, and for fractions of a second down to millisecond or microsecond intervals, various forms of counter circuits, oscillators, and multivibrators are employed. We've got the contact relay, DC operated time delay relays, AC operated time delay relays, time interval measurements, the resistance welding process, automatic sequence timer, synchronous weld control, follow-up or trailing tube circuit, timing the weld, heat control, energy storage welding systems, polyphase welding systems, problems and references. Chapter 17, Electronic Motor Control. Much industrial control equipment requires movement, either rotary or translatory, as its ultimate output. The electric motor, either AC or DC, is the usual means of providing such a mechanical output. The AC motor avoids the complication of separate field supply, and for this reason is frequently employed in the smaller sizes, particularly where controlled speed is not a necessity. In the larger sizes, the unstable speed characteristics and low efficiency of the AC motor have caused the circuit designer to turn to the time-proven shunt field DC motor in spite of the field excitation requirements. The separately excited DC motor has excellent variable speed characteristics and is readily controllable at a good efficiency with electronic circuits. Although a combination of tubes and motors is expensive, it is possible to incorporate other features such as control of speed or torque, current limiting for starting or motor protection, and accurate and simple speed variation, which justify the added cost. Also, the electronic control makes possible the operation of DC motors from the AC lines, avoiding the need for separate DC power generation. This chapter will consider some of the basic electronic principles utilized in electronic control of motors, and will briefly discuss their synthesis in commercial controls. We're off to DC motor relations. Thyratron supply for the DC motor. Speed-torque relations. Speed regulation by armature voltage control. IR drop compensation. Field weakening. Armature current limiting. Auxiliary controls. Speed control by tachometer. Control of low torque AC motors. Phase selective circuits. Problems. References. Chapter 18, Servo Mechanisms. Man, with his inherently slow responses, is a limiting factor on the speed and complexity of many modern devices, and the importance of automatic control to replace him is being increasingly realized. Because of the speed of operation of electronic devices, the electronic art has been frequently called upon in the design of automatic control systems, and these systems now constitute a very large class of electronic applications. Almost all such systems employ feedback, and the methods of analysis are closely allied to those of the feedback amplifier, as developed by Black, Nyquist, and Bode. Because of this unity of thought and method, the analysis and design of servo mechanisms and other control systems are an area of considerable interest to those working in the industrial electronic field. Servo mechanisms and control. First order servo mechanism. A simple idealized servo mechanism system which leads to a differential equation of the first order is shown in figure 18.3. The system is intended to make the output shaft angle theta 0 follow the output shaft angle theta I at all times. The output position theta O is fed back and subtracted from the input theta I to give the error epsilon equals theta I minus theta 0, which serves as input to the amplifier of gain K in torque developed per radian of error input. The output is then a torque of value K epsilon equals K theta I minus theta 0 exerted on the output shaft. Acting as a load on the output shaft is a device with negligible inertia, but with a viscous damping constant or coefficient of viscous friction F. Oh wow, I got lost really fast there. Second order systems. When inertia is included in the simple system, as in figure 18.7, the system becomes a more usual one with the second order equation as a description of performance. The total system inertia referred to the output shaft is J, and F is the viscous friction, any Coulomb or nonlinear friction being neglected as small. Also neglected are any external torque loads. Amplifier gain K is again pound-feet torque per radian of input error angle. Okay. Transient response of a second order system to step input. Derivative control. I think these days they have PID, don't they? Proportional integral derivative. That's not quite what they've got here, but this is on the way to developing that, I guess. Integral control. Oh, there we go. So we got integral and derivative, and we just need proportional. Maybe we had that to begin with. Temperature regulator with integral control. Sinusoidal response of second order system. transfer function analysis, transfer function for multiple loop feedback, transfer functions of several circuits, transfer functions of several physical elements, AC motor servo system, stability, stability criteria, gain and phase margin. Example, further Nyquist plots of the systems, problems, references, index. So the index begins on page 657. And the index finishes on page 666. There we go. Well, I'll throw over the farewell cam. We'll wrap up.
That's a wrap. So that was our book, Engineering Electronics, 1957. They had a little bit about transistors there, didn't they? They called them junction transistors. These days they'd be called BJTs, bipolar junction transistors. And the JFET wasn't discovered yet. So bit of talk about different types of tubes. I've never used a tube. I assume you can still buy them. Probably some of them are more common than others, I imagine. Anyway, that's the end of the video. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.